The superposition theorem says that in any linear electrical network that contains several independent sources, voltage or current, the voltage across or the current through any element equals the algebraic sum of the contributions produced by each independent source acting alone, while all other independent sources are turned off, replaced by their internal impedances. In other words, treat each source separately, find the response, and add the responses together. The theorem only works for linear circuits, where Ohm's law and the principle of proportionality hold. Imagine a set of children pushing a sled on a flat road. The total speed the sled reaches is simply the sum of the speeds each child would have produced if they pushed alone, while the others stood still. The road, the circuit, does not change its nature with each push, it is linear. Mathematically, if V sub I or I sub I is the voltage, current caused by the ith independent source S sub I with all other independent sources deactivated, then the total voltage current V total I total is V total equals the sum from I equals 1 to n of V sub I, and I total equals the sum from I equals 1 to n of I sub I. Explanation, conditions, and limitations. Linearity: every element must obey a linear relationship between voltage and current. Ohm's law: linear inductors, linear capacitors. Nonlinear devices such as diodes, transistors, or saturated cores break the theorem because the response is not proportional to the source magnitude. Independent sources only: the theorem is applied by deactivating independent sources. Dependent, controlled sources remain active because they depend on circuit variables, not on an external ideal source. An independent voltage source is replaced by a short circuit, 0 volts ideal wire. An independent current source is replaced by an open circuit, 0 current break. Frequency independence: for linear time invariant circuits, superposition works at any single frequency. In AC analysis, you can apply it to phasor quantities, but you must keep phase angles consistent. Power cannot be superposed. While voltages and currents add linearly, power, which is quadratic, does not obey superposition. You must compute power after finding the total voltage or current. Step-by-step algorithm. Identify all independent sources in the circuit, both voltage and current. Write down their values. Choose the target variable you want, voltage across a resistor, current through a branch, etc. Create a copy of the original circuit for each independent source. Deactivate all other independent sources in that copy. Replace voltage sources with a short circuit. Replace current sources with an open circuit. Analyze the reduced circuit using any preferred method: Ohm's law, mesh analysis, nodal analysis, the Venn or Norton, etc., to obtain the contribution of the active source to the target variable. Record the contribution, including sign and direction. Repeat steps 3 to 6 for every independent source. Sum all contributions algebraically to obtain the final answer. Verify by solving the original circuit with a single method, for example, nodal analysis, to check consistency. Tip: keep a clear notation for each contribution, such as V sub R superscript V1 for the voltage across resistor R caused by source V1, and V sub R superscript I2 for the contribution from current source I2. Analogy: think of turning off all lights in a house except one, measuring the brightness in a particular room, then doing the same for each light individually, and finally adding the brightnesses together. Explanation: mathematical illustration using linear algebra. Consider a simple resistive network with 3 nodes excluding the reference ground. Let the node voltages be V sub 1, V sub 2, V sub 3. The circuit has 2 independent sources: a voltage source V sub S between node 1 and ground, and a current source I sub S injected into node 2. Using nodal analysis, the KCL equations can be written in matrix form. G bold times V bold equals J bold, where G bold is the conductance matrix. V bold equals a column vector of V sub 1, V sub 2, V sub 3, and J bold is the source vector. Suppose the conductance matrix is G bold equals a 3 by 3 matrix with entries. First row G sub 11, negative G sub 12, 0. Second row negative G sub 21, G sub 22 plus G sub 23, negative G sub 23. Third row 0, negative G sub 32, G sub 33. The source vector is the sum of contributions from each independent source. J bold equals J superscript V sub S plus J superscript I sub S. Contribution of the voltage source V sub S. Deactivate the current source, open circuit, yields J superscript V sub S equals a column vector of G sub 11 times V sub S 0, 0. Contribution of the current source I sub S. Deactivate the voltage source, short circuit, yields J superscript I sub S equals a column vector of 0, I sub S 0. Solve two linear systems. G bold times V superscript V sub S equals J superscript V sub S, and G bold times V superscript I sub S equals J superscript I sub S. Then the total node voltages are V bold equals V superscript V sub S plus V superscript I sub S. Because the conductance matrix G bold is the same for both systems, the superposition principle is reflected mathematically as the linearity of the matrix equation G bold V bold equals J bold. This demonstrates that the response, node voltages, is a linear combination of the source vectors. Worked example 1, 2 voltage sources. Circuit, 3 resistors R1 equals 2 ohms, R2 equals 3 ohms, R3 equals 5 ohms form a triangle. Node A is connected to a 10-volt source VS1, positive at A, reference at ground. Node C is connected to a 6-volt source VS2, positive at C. We need the current through R2, the side between nodes B and C. Step 1, choose target I sub R2. Step 2, source 1 active, source 2 deactivated. Deactivate VS2, replace with a short between node C and ground. The circuit becomes a simple series parallel network. VS1 equals 10 volts drives current through R1 to node B, then splits between R2 and the shorted R3. Calculate equivalent resistance seen by VS1. Rec equals R1 plus the parallel of R2 and 0, which equals R1 plus 0 equals 2 ohms. Because a short makes R3 0, forcing all current through the short path, leaving R2 unloaded. The total current from VS1 is I total equals 10 divided by 2 equals 5 amperes. Since node C is shorted, no voltage appears across R2. Therefore, I sub R2 superscript VS1 equals 0. Step 3 is source 2 active, source 1 deactivated. Deactivate VS1, replace with a short between node A and ground. Now VS2 equals 6 volts drives current through R3 to node B, then splits between R2 and the shorted R1. Equivalent resistance. Short across R1 makes its resistance 0, so all current goes through the short, leaving R2 again bypassed. Hence I total equals 6 divided by 0 appears infinite, but physically the short forces node A to ground, so the voltage across R2 is 0. Therefore I sub R2 superscript VS2 equals 0. Step 4, sum contributions. I sub R2 equals 0 plus 0 equals 0 amperes. The result matches intuition because each voltage source creates a shorted path that bypasses R2, no current flows through it. Real-world analogy. Think of 2 water pumps feeding a pipe that has a side branch, R2. If each pump opens a direct bypass pipe that shortcuts the side branch, no water flows through the side branch. Verification. Solve the original circuit with mesh analysis. You will also obtain I sub R2 equals 0 amperes. Step 1, identify sources. One independent voltage source Vs equals 12 volts, one independent current source Is equals 3 amperes. Step 2, contribution of Vs only, deactivate the current source, open circuit. The bridge reduces to a simple voltage divider. The left side sees R1 in series with the parallel of R2 and R3, the right side is R4 to ground. Compute equivalent resistance of the parallel branch. R23 equals R2 times R3, divided by R2 plus R3 equals 6 times 8, divided by 6 plus 8 equals 48 over 14 equals 3.43 ohms. Total series resistance from source to ground. R total equals R1 plus R23 plus R4 equals 4 plus 3.43 plus 10 equals 17.43 ohms. Current supplied by the voltage source. IV equals 12 divided by 17.43 equals 0.689 amperes. Voltage drop across R1. VR1 equals IV times R1 equals 0.689 times 4 equals 2.756 volts. Voltage at the top node between R1 and the parallel branch, is V top superscript Vs equals Vs minus VR1 equals 12 minus 2.756 equals 9.244 volts. Step 3. Contribution of IS only. Deactivate the voltage source, replace with a short circuit between left node and ground. The circuit now is a pure current source feeding the bridge, with the leftmost node at ground. We can use node voltage method. Let the top node voltage be VT unknown and the bottom node voltage be VB ground because the short ties the left side to ground via R1 and R4. The current source injects 3 amperes into the top node. KCL at the top node. 3 equals VT divided by R1 plus VT divided by R2. Since VB equals 0 ground, this becomes 3 equals VT divided by 4 plus VT divided by 6. Find common denominator 12. 3 equals 3 VT over 12 plus 2 VT over 12 equals 5 VT over 12. Thus VT equals 3 times 12 divided by 5 equals 7.2 volts. So V top superscript IS equals 7.2 volts. Step 4. Superpose. V top equals V top superscript VS plus V top superscript IS equals 9.244 volts plus 7.2 volts equals 16.444 volts. Note, because the two sources are connected to the same reference ground, their voltages add directly. Verification. Solve the full circuit with nodal analysis, both sources present, and you obtain the same 16.44 volts at the top node. Analogy. Think of two workers pushing a car from opposite sides. One pushes with a constant force voltage source, while the other adds a burst of pushes at a steady rate current source. The car's final speed node voltage is the sum of the speeds each would have given alone. Result: the top node voltage is approximately 16.44 volts. Common pitfalls and how to avoid them. 1. Wrong deactivation. Replacing a voltage source with an open circuit or a current source with a short is the opposite of the correct rule. Remember, voltage source leads to short, current source leads to open. 2. Forgetting dependent sources. Dependent controlled sources must stay active. Turning them off destroys the relationship that defines them, leading to wrong results. 3. Sign errors. When summing contributions must keep their algebraic sign direction. Use a consistent current direction or voltage polarity throughout. 4. Double counting. After finding each contribution, do not reapply Ohm's law with the total source values. Simply add the contributions. 5. Mixing AC phasors without keeping angles. In AC analysis, keep magnitude and phase together. For example, 10 angle 30 degrees volts. Adding only magnitudes gives wrong phasor sum. 6. Assuming power superposes. Power must be calculated from the final total voltage over current, not from individual contributions. 7. Neglecting source internal resistance. Real sources have internal resistance. When deactivating, replace the source with its internal impedance, not an ideal short or open unless the internal resistance is 0. How to avoid: write a checklist before you start. Identify source type, write deactivation rule. Keep dependent sources untouched. Mark current voltage directions on a sketch. After each sub-analysis, note the sign of the result. Perform a quick sanity check, for example, expected direction, magnitude, range. State the superposition theorem and list the 2 rules for deactivating independent sources. The theorem says the response in any linear circuit equals the algebraic sum of the responses caused by each independent source acting alone with all other independent sources turned off. Deactivate. Voltage source becomes short circuit. Current source becomes open circuit. A circuit contains a 5 ohm resistor in series with a 10 volt source and a parallel branch of a 2 ohm resistor and a 3 ampere current source. Find the current through the 5 ohm resistor. Analyze with source 1 only, 10 volts, current source open. Compute total resistance. Current equals 10 volts divided by the sum of 5 ohms and 2 ohms, which is 1.43 amperes. Analyze with source 2 only, 3 amperes, voltage source short. Current splits. Through the 5 ohm resistor equals 3 amperes times 2 ohms divided by the sum of 5 ohms and 2 ohms, which is 0.857 amperes. Sum the contributions. Total current equals 1.43 amperes plus 0.857 amperes, which is 2.287 amperes. A circuit has 2 meshes, each containing a 12-volt source and a shared 4-ohm resistor. Find the mesh currents. Treat source A alone and deactivate source B by shorting it. Solve mesh a current as 12 volts divided by the sum of 4 ohms and the series resistance. Then repeat for source B, add the two mesh currents to obtain the final values. A circuit contains a 10-volt angle 0 degrees sinusoidal source and a 5 ampere angle negative 90 degrees current source feeding a network of 10 ohm resistors. Determine the voltage across a particular resistor. Convert each source to a phasor, deactivate the other by shorting or opening as appropriate, solve using impedance. Since the network is only resistors, the impedance is real. Keep the complex results, add the phasors, and convert back to magnitude and phase. Power calculated from individual source contributions can be summed to obtain total power in a linear circuit. False power is a quadratic quantity, only voltages and currents superpose. Extension to circuits with dependent sources. When a circuit contains dependent controlled sources, the superposition theorem still works, but the rule changes slightly. Treat each independent source separately as before, deactivate the other independent sources. Leave all dependent sources active in every subanalysis, because their values depend on circuit variables, currents, or voltages that may change when an independent source is turned on or off. After solving each subcircuit, add the obtained responses. A procedure example. Circuit, a voltage-controlled current source VCCS. I sub C equals G V sub X, where V sub X is the voltage across resistor R sub X. The circuit also has an independent voltage source V sub S and an independent current source I sub S. Goal, find the voltage across R sub 1. Step A, source V sub S active only. Open circuit I sub S. Write KCL KVL, including the VCCS term G V sub X. Solve for V sub R1 superscript V sub S. Step B, source I sub S active only. Short circuit V sub S. Keep the VCCS active. Its controlling voltage V sub X will now be a function of I sub S. Solve for V sub R1 superscript I sub S. A step C is sum. V sub R1 equals V sub R1 superscript V sub S plus V sub R1 superscript I sub S. Numerical illustration. Let R sub 1 equal 1 kilo ohm, R sub X equal 2 kilo ohm, G equals 0.001 Siemens. V sub S equal 5 volts, I sub S equal 2 milliamps. With V sub S only, I sub S equals 0. The VCCS current equals 0.001 times V sub X. Solve the simple two-node network. V sub R1 superscript V sub S equals 3.33 volts. With I sub S only, V sub S equals 0. The VCCS current equals 0.001 times V sub X, where V sub X equals I sub S times R sub X equals 2 milliamps times 2 kilo ohm equals 4 volts, so the VCCS supplies 4 milliamps. Total current through R sub 1 equals I sub S plus 4 milliamps equals 6 milliamps. V sub R1 superscript I sub S equals 6 milliamps times 1 kilo ohm equals 6 volts. Sum V sub R1 equals 3.33 volts plus 6 volts equals 9.33 volts. Thus, even with a dependent source, superposition works once we remember to keep those sources alive in every subcircuit. The key intuition is that dependent sources are like internal helpers that react to whatever independent source is present. Turning them off would erase their contribution completely and give a wrong answer.